Okay, so here's the last video for this unit. So this is going to focus on the energy of simple harmonic oscillators. So one thing to note is that objects that undergo simple harmonic motion still follow conservation of energy. Okay, so that's still going to hold true no matter what, right? So they're going to have, they'll have, they'll have maximum potential energy when the displacement is at its maximum. Okay, so when it's further away from its equilibrium position, it's going to have all potential energy. Okay, so for pendulums, the energy is going to be gravitational potential energy, and for springs, it's going to be elastic potential energy. Right, and so if you recall those equations from when we talked about energy, UG is mgh, US or elastic is going to be 1/2 kx squared. Okay, so those are going to come into play, right? So the maximum kinetic energy is going to occur at equilibrium, and this is because this is where the maximum velocity occurs, right? And so this is where it's all kinetic energy, not potential energy. Now, some ways that you can, and these blanks should not be here, I apologize for that. So you can have bar charts, right? Or simply graphs are the best, most basic way to visualize the data. And for us, there's two really important graphs that you could see pop up in the test. The first one is what we call energy versus time, where this shows us how energy changes over time. And then the other thing is energy versus position. And this will tell us how energy changes, or as the object changes its position. All right. And so the first graph that you see here, I'll zoom in so we can look at this a little bit. Right. And so if we just remember principles about energy, so this is going to be our energy. Oh, sorry. So this here is our energy versus position. So this line here is our potential. Let's say this is a pendulum, right? So that's our potential energy. This is our kinetic energy, right? How do we know? Because it's a max at the extremes, right? So if these here are extremes, when theta, you can tell this is a pendulum because it's theta max, okay? And then you can also look at how the here the kinetic energy is 0 at the extremes, right? And so here potential energy is 0, so UG equals 0. Kinetic energy is max. But notice that they're basically the same curve, just flipped on top of each other, right? But remember, with energy, the one thing that does not change is that total energy. I know it's kind of this graph probably should extend a little bit further up, right? And so the total energy does not change. Okay. Now this one the next graph over here to the right, this is our energy versus time. And you can see this is very sinusoidal, right? The sine curve. This is our potential energy. The blue one is our kinetic energy, right? But you can see it alternates like max, min, right? So max, min, min, max, right? But what doesn't change? If I take those at any point in time and I add them together, it equals the same thing. Okay. So those are the two kinds of graphs that you can really look at. So let's look at some example problems um, for simple harmonic motion and energy. So this is a pendulum length 1.5 meters, as a bob of mass 0.100 kilograms is displaced 10 degrees from the horizontal and released. A, what is the total mechanical energy of the pendulum? B, what is the speed of the pendulum as it passes through the lowest point of its motion? And now, so this is what they like to do on the AP test. They combine it with another topic. So this is, suppose the string breaks to when the bob is at its lowest point. What is the horizontal distance the bob will travel if its height above the floor is at this point is 0.75 meters? So if we draw a physical picture, it's going to start like this, right? Swing down, and then this is going to break, and the bob is going to move off in projectile motion, right? Something that looks like this, right? In fact, I don't need this part because what I can do is say at this point this is going to break. Oh, go back. So at this point it's going to break, and then tell us this is 0.75 meters. Right, there's my ground. Okay. And so what we need to do is find the total energy. We need to find the speed, and then we need to find where does it land, right? So where does this land? Okay. So the first thing's pretty easy. We know at its extreme, it's going to be all potential energy. So we know for part A, E is going to be K plus U. But we know we're at our extreme, so K is going to be 0, and it's going to be just simply mgh. But how far, like what is this height, right, from here? Okay, and that's where we had that shortcut formula of h equals l minus l cosine theta, right? That's where that can, or that's where this is going to be handy. So we're going to do 1.5 minus 1.5 cosine 10 degrees, and so this gives us a height of 0.0228 meters. And so now I can just plug that in. So 0.100 kilograms, 9.81 for G, and now my height that I calculated by using that formula. So the total energy of the system is going to be 0.224 joules, or you can write it as 2.24 times 10 to the negative 2 joules. Okay. Now, part B is what is the speed at its lowest point. Well, you have to remember the speed at the lowest point, right? Or the lowest point is where it's all kinetic. So here we are at our lowest point. This is going to be 0, and it's just going to be equal to 1 half mv squared. And so I'm going to solve this for v. So it's going to be the square root of 2e over m. And so it's going to be the square root of 2 times 0.0224 over the mass of the bob, right, 0.1000, and it's going to give me a velocity or speed of 0.669 meters per second. Okay, now part C is when we do the projectile motion part. So part C, the first thing we need to do is go way back to projectile motion, right? So it's a horizontally launched object. So our equation for vertical displacement is 1 half gt squared. So I'm going to solve this for time. So it's going to be square root of 2y over g. And so it's going to be the square root of 2 times 0.75 times 9.81. And so it's going to take me 0.391 seconds to go down. And then I go and do my x equals VOT, where this is my VO, right? So it's going to be 0.669 times 0.391 seconds. And I'm going to have an x distance of 0.262 meters, right? So it's going to land 0.262 meters away. So again, this problem is very, the AP likes to use different or combine the different topics, okay? Now in this one, we're gonna look at a mass spring system. So this is a 0.600 kilogram mass. The end of the spring vibrates 3 times per second with an amplitude of 0.13 meters. Determine the velocity when it passes the equilibrium point, the velocity when it is 0.100 meters from equilibrium, and then the total energy of the system, okay? The first thing we need to do is we need to figure out two things. We need to figure out the period, and then we need to figure out the K value, okay, of this spring. So the period, it tells us that it does 3 times per second. And so actually that'll give us the frequency, right? So 3 times per second, okay, is our frequency. So if we want to make this period, we're just going to do 1 over 3, right? Because of the inverse relationship. So it's 0.333 seconds is going to be our period. Now, what that does is it allows us to solve for our K value. Okay. So we're going to end up with something like when we did before, when we did the G value on the planet in the last video. It's going to look something similar to that 4 pi squared L over T squared. But we're going to now have our spring info. So it's 4 pi squared M over T squared. Again, make sure you're squaring these two. So you can do 4 pi squared times the mass, 0.60, divided by T, which is 0.333. We're going to do that, and we're going to find that K is going to be approximately, and I'll round it, 220 newtons per meter. Okay. Now it's going to allow us to find part A, which is what is the velocity as it passes equilibrium. And so if we do energy before equals energy after, before it's only potential, so it's elastic, and after it's kinetic. So we'll do 1/2 kx squared equals 1/2 mv squared. And we solve this for v. It's going to be kx squared over m, and we're going to take the square root of that. So it's going to be the square root of 220 times x squared times 0.13, because that's our maximum x, right? This is where it's like elongated completely, divided by the mass. Okay, and so that's going to give us approximately 2.5 meters per second. Okay, now part B talks about the energy at 0.10 meters from equilibrium. Well, again, we're going to say E before equals E after, right? Now you could do a couple things. You can use, 1/2 mv squared, on your before side. So I can also use 1/2 kx squared, but the after side, or one of the sides, has to be the sum of the the kinetic energy and the elastic potential energy. But again, the good thing is these 1/2s go away, and you do a little bit of algebra, you're gonna end up with, so this is initial, final. So I'm gonna end up with the square root of kx squared final, or initial, sorry, minus kx squared initial, sorry, final, sorry, I got them backwards, divided by mass. Let me rewrite that. It's a little messy. Okay, so I often think that I'm just using a piece of paper. So it's gonna be square root of k. I'll factor it out. X squared minus x initial squared minus x final squared divided by the mass. So it kind of looks like that kx squared over m, but we have initial minus final. And so it's going to be 220 times 0.13 squared minus 0.10 squared divided by 0.60. Okay, and so you plug this into your calculator and you get a speed of 1.58 meters per second. Okay, so that's the speed, 0.10 meters from equilibrium. Now, part C, what is the total energy? We actually could have done this to start by just simply doing 1/2 kx squared, right? But we could also do the two velocities, right? But let's just do 1/2 kx squared. So 1/2 times 220 times 1.13 squared, and it's going to be a total energy of 1.84 joules. Okay, and if you go back and you do like 1/2 mv squared, right? Sorry, yes, 1/2 mv squared at the equilibrium. So you would do 1/2 times 0.60 times 2.5 squared, and guess what you end up with? 1.84, right? Maybe a little bit different rounding. Do the same thing here, just by doing this part, 1/2 kx squared final kx final squared plus 1/2 mv squared, and you're going to end up with 1.4, right? So part C, you can really do it three ways. You could even do this first and then work your way back to A and B, whichever one you want to do. But that is unit 6. Unit 6, again, remember, is a very short unit. We're focused on really two things: the period of an oscillator and the energy of an oscillator. Okay, looking forward to unit 7. Unit 7 is rotations, where you could see some of this pendulum stuff again. All right, thank you.